Our first speaker is Professor Terry Turney, who is CTO of Sonic Essentials, a micronutrient fertilizer manufacturing company, and also CTO of Micronisers Australasia. So they specialise in a diverse range of nanoparticle manufacturing. Terry was previously a chief scientist in the materials division and director of the Nanotechnology Centre at CSIRO. He has an academic position in the Department of Materials Science and Engineering at Monash University. Terry's R&D interests include polymeric nanocomposite materials and applications of nanoparticles and nanocomposites within sustainable manufacturing, healthcare and personal care products. Outside of work, Terry is a passionate gardener and plant collector. And I personally, as Adele said, am very fortunate to have Terry as one of my supervisors for my PhD and to have the opportunity to learn from his extensive expertise. So let us welcome Terry to the stage. I will stop sharing. And Terry, if you would like to share your slides.
Thank you for the kind words. It's so unusual to hear kind words from you, Tessa.
Oh, come on.
Right? No. Tessa and I get on quite well. We insult each other with regular everyday abandon. I'm going to talk about biomaterials, biomimetic materials. It's a key part of biomimicry. It is because nature operates at so many different length scales, from the atomic right through to the ecosystem level. So you're looking at 10, 12 orders of magnitude in different lengths. I want to talk about the nano area, just a bit above the atomic, the chemical area, basically, for the most part. Well, I want to talk about biomimetic materials. What I'd like to do is to give you some examples of how nature uses materials in a way that we should be able to mimic. I've got the slide up here with an image in front of you. That is a fly. It's actually a colorized scanning electron microscope image of a fly. I love this image. If you think about this, how can this animal eat some garbage, eat some trash, and end up with such a beautiful structure? We don't know how to do that. I would love to be able to make a structure as complicated and as elegant as that. We've got a long way to go. So I want to talk about how we can maybe start to get there. If you look at where we are right now, our current industrial system is really only 250 years old. Really, it's based on the industrial revolution that happened initially in Europe in the 1700s. If you think about it, then it depended on it, and it still depends on fossil energy sources. It depends on petrochemical feedstocks for most of our, certainly organic chemicals we use. It uses heat and pressure to process for the most part. It does. It's very materials intensive, it is. And it's extremely inefficient. All of those things are the things you don't want it to be. But unfortunately it is, and we need to see how nature does things. Because if you think about it, nature is probably the best materials engineer and best materials scientist. And what we'd like to be able to do is we should be inspired by solutions that's been perfected by nature through natural selection. It's been doing this successfully for 3.5 billion years. So how does it design things to not have to go through the intense energy processes and fossil fuel processes that we go through right now? So how can we learn from this? That's what I'd like to talk about. But maybe I should start off with some examples. This is a close-up of that fly's eye, and I want to talk about the eye a bit in more detail. Here is an individual. Oops, what happened here? I've lost it. Apologies. Let's see if I can get back to it again.
We can still see it, Terry.
Can you? Okay, well, I can't.
Uh-oh.
There, I'm back now. Okay, it's all right now. This is one of the light receptors, basically, one component of the compound eye. And it's interesting, it's actually got these little bumps on the surface, and it's got all these ridges along the edges. What the fly is doing here is trying to optimize the amount of light that hits the retina here. The bumps on the surface are actually an anti-reflection coating. It actually stops the light from bouncing off the eye and out again, because you want to get as much light as possible through this structure onto the retina. These ridges are actually an animal equivalent of a Fresnel lens. Is basically what they do is they will focus the light that comes in at an oblique angle onto the retina. So this is a really elegant solution to optimize the amount of light that goes into the fly's eye. It's done with other animals. It's quite a common phenomenon. The cicada, for example, does this, and you can see these little bumps on the surface of the cicada. There's two different types of cicadas here. You can see that and what this is doing in the case of the cicada is it's stopping reflection coming off the wing. So if you're a cicada, you're flapping around, it's a Jersey little feed for a bird. So you don't want these little shiny mirrors flying around when you're flying, so the birds can see you. It has other effects as well. It can actually act as a anti-reflection coating. It acts as an antibacterial coating as well. It's also waterproof. Water doesn't stick to it. It's an anti-wetting coating. And the reason this works in the case of the cicada is the refractive index difference between the two media. In this case, air and the chitin of the cicada is quite substantial. And the only way that the cicada can actually stop the reflection which occurs because of refractive index is by having these small bumps on them. We do this. If we actually thought about this a bit more a few years ago, we could have actually worked out, if you want to make anti-reflection coatings, you coat glass with this type of structure. And it works really well. It does. And now people do this quite commonly. And the inspiration for this is for manifold applications. If you want to have a solar cell, you want to maximize the amount of light that gets onto the photovoltaic elements of that cell. You don't want reflection occurring off the surface of the cell. This is one way of increasing the efficiency. Increasing efficiency with 3 to 5% of a solar cell. For an LED, where light is coming out of the device, you can again improve it by 3 to 5% by having this coating on the outside of the LED device, so that it then lets all the light through. Camera lenses are being used. These are self-cleaning, these surfaces. They're anti-fogging surfaces. And I'll talk a bit more about this. They're also antibacterial surfaces. Now, we can make these. There's a whole range of different ways of making them. And one of them is actually looking at things like nanoscale or colloidal printing. And we can do this at a sub 300 nanometer level. So this is it's a sub-wavelength anti-reflection coating. You've probably come across something like this before if you have any interest in biomimicry. The example everyone uses with biomimicry is the lotus effect, the surface nanotexturing that occurs with the lotus, where the lotus leaf will actually not wet, and that water sits on the surface of the lotus leaf. And it does that by a similar process. It basically has a series of bumps on there, and the droplet of water can actually wet the surface because it sits proud of those bumps. It does, the little pillars on the surface. Exactly the same thing is happening with the cicada wing. It actually stops the cicada wing from wetting as well, or the fly's eye in that purpose as well. You can change this. If you think about this, you've got a lot of things you can change here. You can change the size of the height of these pillars. You can change the distance between the pillars, and you can change the size of the pillar itself. In the case of a lotus leaf, it does other things as well. You actually can chemically coat the pillar with a waxy-like substance. There's a lipid coating on the surface of this pillar, and there can also be a lipid coating the substrate under the pillar as well. So you've got all these ways of changing the nature of the interaction between, say, water and the surface. You can change those parameters. You can actually make the surface super wetting rather than super water repellent. So you can make super hydrophilic surfaces where that surface will actually trap the water. So by looking how nature does this, then you can actually start to see a whole range of applications we can use for this as well. And it's similar in some ways to what a water strider can do. A little fly sitting on, or an insect sitting on the water surface. The surface tension of the water keeps it floating. Same here. The surface tension of the water, the surface energy is such that it actually doesn't wet the surface in the case of super hydrophobic coatings. I want to talk about this beetle. This is a beetle that lives in the Namib Desert, in the desert in Namibia. It's a desert there. It's on the Atlantic coast in southern Africa. It's a very dry environment. There's no water. Basically, it's very, very really rains. So, but what it does do is there's a whole range of fogs that come in every morning from the Atlantic Ocean. So what these beetles do is they climb up the top of the sand dunes, stand on their head basically with their bottoms up in the air, and collect the fog. And they do this because they've got a mixture of super hydrophobic and super hydrophilic coatings on their overwings. So animals use this quite extensively. We can do the same thing. In fact, in Chile, there are now fog capturing devices near the Atacama Desert, where the Atacama Desert meets the Pacific Ocean, and people collect water this way as well. So you can get inspired by how nature solves these problems to actually come up with a practical solution for ourselves. And this works because the water and the fog gets trapped on these surfaces, and it wicks down into a vessel which you can collect. Right. So you can use this type of controlled energy, surface energy, for looking at clean, self-cleaning textiles and surfaces, looking at fog hubs, let's say. If it's super hydrophobic or super hydrophilic, you can actually look at changing fluid drag, say in pipes. You could look at shark skins. Sharks use this type of technique in order to decrease to improve the hydrodynamic flow. Ships can use this type of coating in order to decrease drag in water. The coatings are also interesting. There are quite a few companies out there making these coatings now as antibacterial coatings. What happens when they're super hydrophobic like this is that they can't, bacteria and microbes actually can't adhere. So it actually is a way of preventing bacterial contamination of surfaces without having to use antibiotics and other toxic chemicals. And that's being used now for coating of catheters, for example, using medicine. It is. So there's a whole range of novel applications here. So from a simple thing like the lotus effect or the cicada's wing or a fly's eye, you can start to see, you can get inspired for a whole range of different applications here. You could use it for water wicking. It's not been published yet, but people are now starting to look at this as for two-dimensional pumps, for liquid pumps, where you can actually make water and other liquids flow in one direction with an electric, with a very small electric charge. That's being developed. It's still a ways off from being an active 2D pump. I want to talk about a different type of color. Now, I want to talk about color. Color is a problem. Color in nature is not too bad. We've got pigments, right? We've got chlorophyll, the green pigment. We've got anthocyanins, which are the purple pigments you see in blackberries and cherries and dark flowers. Carotenoids, and carrots, the orange pigments. And we make fossil fuel derivatives. So most of our dyes are actually fossil fuel based, right? And that's the type of color that we can use. So this is now a different example. I want to leave the issue about phobicity of surfaces and just talk about color. There's a different type of color which is available, a second type of color which is available. And it's a diffractive color, it's a structural color. You're familiar with this you think about an opal, the silica spheres and the silica in an opal is actually colours. It's white. What you're seeing here is diffraction patterns coming off an ordered arrangement of the small spheres of silica. And that's what gives the colour to the opal. Bird feathers, the peacock's feather is a structural colour. It is. It's not a dye. It's caused by the structure on the feathers. It is, and they actually act as diffraction patterns, and they will selectively diffract one particular light wavelength and block the others. Beetles do this. If you look at a beetle, a beetle is a boring insect. It's actually it's made out of chitin, and the wing cases are made out of chitin and melanin, and they're brown. The reason that all of these animals aren't brown is because of the order between the chitin and the melanin, and they form diffraction gradients. They do, which give you this colour. You can see this here. I'm actually showing you here. You can see these lines. They're alternating lines of melanin and chitin. And an animal like this, right? Structure, compositionally, it's just chitin and melanin, right? You get some different colours because the differences between the width of each layer and the distance between the layers can be changed. And so you can actually look at this to diffract a certain amount of green light or a certain amount of red light selectively, blocking all the others. So this is actually, it's called a quarter wave plate, but these spacings are about 140 to 160 nanometers. Tessa sent me this morning. This is Tessa's pet beetle. It is. You can see it here as well. I thought I'd put that up there for you, Tessa. We can do this quite well. We can do this in 2 dimensions really quite well. 3 dimensions are a different issue. In 2 dimensions quite well. These are optically variable devices. You're probably familiar with these. If you look, most countries' banknotes have got optically variable devices on, holograms. Your bank card's got hologram on. These 3 images are actually the same pattern. The only difference between them is the light is coming in at a different angle. So we can actually get very sophisticated 2D optically variable devices. So that's actually the same pattern, but just with different illumination directions. What we can't do very well is to make 3-dimensional structures. And this is a real problem for us. One of the biggest issues with our dyes that we use are the red dyes. These red chemical dyes fade in sunlight. They undergo photooxidation. It's a real problem. If you can make a diffractive pigment, it would never wear out because it's not being affected by sunlight. It's a diffraction grading. As long as the structure stays intact, it won't fade. If you can make special and opalescent pigments as well from these types of structures, the same way as an insect does. We're not quite there yet, but it's quite a problem for us. I mean, you can see some opalescent pigments which are being made on cars nowadays. But if you look at, say, a red pigment or a red dye that's added to plastics, you can see if it's an old car, for example, these are brake lights on old cars, they go yellow over a series of over a few years. It's a problem. We actually don't have very good red dyes, or certainly as plastics additives. If you could come up with an attractive pigment, that would be really neat. Right? So people are working on this quite actively at the moment to try and get them, but we still haven't quite got there yet. It's mimicking what nature does. I want to talk about a different type of scattering now. I want to talk about this this insect. It lives in the understory on the ground in Malaysia. Cyphocylus. There's a whole range of species of this, but this one actually its main food is a white fungus, and that's why it's white. Right? It's a mechanism against predation. Right? If a bird scraps around in the undergrowth, hopefully it doesn't see the insect, so it doesn't become dinner for someone. this white pigment is really interesting. It's highly disordered. So what happens? It doesn't selectively scatter light. It selectively scatters all wavelengths of light. It doesn't just selectively scatter one wavelength of light, give you a color. So it totally scatters everything. And the reason it can do that is in between these scales, where the individual scales, which are only about 5 microns thick, the structure is totally disordered. It is. So any light that hits that would bounce back. And again, it bounces back because the difference in refractive index between the light, it's an interfacial thing. It's the difference between refractive index of chitin and of air, basically. So that any time it sees an interface, it will actually the light will bounce back. How can we use this? Well, these white pigments would be really good. It'd be really neat to make these white pigments. They're very thin. They could replace paint. The titanium dioxide that is currently used in paints, we make about 4 to 5 million tons a year globally. Titanium dioxide is a really nasty thing to make. You take crude rutile and then you treat it with chlorine gas at elevated temperatures, and you distill off the titanium tetrachloride that you purify. And having done that, you then have to burn that titanium tetrachloride in a pure oxygen flame at 1200 degrees centigrade to make this. And we make it this way. This is called the chloride process. We make 4 to 5 million tons of this a year that way. And when you've made that paint, the problem is that the paint, in order to be able to give good hiding power to whatever the surface is underneath, usually the film is around at anything up to 100 microns thick. Look what the insect's doing. 5 microns, totally white. Can we come up with a 5 micron paint that will actually hide under the surface underneath? This is a target that people are looking at right now. We're trying this with porous polymers, with cellulose nanofibers, with white kaolin clay particles. This is a whiter than white. So there's an inspiration here. Can you actually do what nature does in a way that would be less environmentally disastrous, frankly, in this case? I don't know. It's worth looking at white colours. Again, I'm saying that white flowers have got almost no coloured pigments, and all the light from their petals is scattered because of the disorder in the petal. They have small air pockets in the cellulose of the petal. In this case, it's not chitin, but cellulose in the plant, and that causes the scattering of light in all different directions. Well, that's really neat, and the reason this could do this is that these pockets are basically are closed to closed. They are, so if it gets wet, they still stay white. This plant's quite interesting, Diphylia grayi. This is also showing white scattering, but if it gets wet, that's what happens to it. The water can get in between into these little gaps, the air gaps in between the cellulose fibers, and because the refractive index of water and cellulose are very similar, it actually becomes transparent. When it dries out, it goes back to being white again. I think this is a neat plant. I've actually got some of this growing in my garden. I'm still waiting for it to flower to actually see this. I'd like to have been able to show you this, but I can't. So these air pockets, when they get filled up with water, they stop scattering light effectively. And they effectively become transparent because the refractive index is matching. Inspiration here for things: smart windows, camouflage. People are talking about clear umbrellas. I think this is not the best place to go, but people are looking at using this for anti-counterfeiting, modifying the structures for sensing, information storage, QR codes. If you can imagine, a QR code would change when it got wet, and it wouldn't have to be water. It could be another. It could be another material, another liquid. So you could think of a whole range of ways of using this type of strategy that nature uses quite effectively. I'm going to stop now because I've only got basically a few minutes available to me, and I want to talk about I want to talk about the difference between natural and industrial ecosystems. I do. The industrial processes, I said at the very beginning, been going for about 250 years. Natural processes have been going for 3.5 billion years. So they've been around for a while. And nature's had a lot of time to get it right, whereas we've done a pretty poor job in our 250 years. Most of the periodic table we use nearly every element of the periodic table somewhere or other in our manufacturing processes. Nature only uses a very few elements, mainly carbon, hydrogen, nitrogen, oxygen, with some trace elements, but mainly those. We're dominated by thermodynamic control and energy consuming assembly. We are. And we've basically got, I call this a heat and beat economy. Nature doesn't do this. Nature's dominated by kinetic control, self-assembly. It looks at information and structure. That's how it embeds the colour, say, for example, in insects, and how it controls the surface of cicada wings or a fly's eye in order to be able to get the type of structure. These are not being done at high temperatures or high pressures. It's green manufacturing in practice. We have a centralized manufacturing process. It's energy inefficient. But I think the person that did the most damage in the past 150 years was Henry Ford. And it was the invention of the assembly line. So what we do now is we bring resources, feedstocks from all over the world into a central spot, make our car or our piece of plastic or whatever it is. And what do we do with it? We send it all over the world again. It's very inefficient distribution of feedstocks and products. Nature doesn't do that. Nature manufactures in situ. It uses and recycles in situ. And it uses ecosystem services to do this. So nature has a decentralized manufacturing strategy. We have a centralized manufacturing strategy. That's a big difference. What we do is very linear. We don't have many feedback loops. If we can't get one of our resources, one of our feedstocks, it stops. The whole process stops. We can't manufacture the car or the plastic. But natural ecosystems are different. They're non-linear. They've got lots of feedback loops and they're resilient when they're under stress. It's a big issue for us. I don't think we've actually put enough emphasis on the difference between our system and the natural system. We use things once. We do. It's a once-off usage. So we've got an extremely high materials and energy wastage. It's basically a rubbish economy. If you think about it, everything we make actually goes to waste. I mean, a takeaway coffee cup might be used for 15 minutes and it's thrown away. The concrete in the building might be used for 200 years, but it's thrown away. Everything we use is, well, nearly everything we use is basically goes to waste eventually. Nothing goes to waste in industry at an ecosystem level. Because waste from one part of the ecosystem is a resource to another part. It is a true circular economy. That is the difference as well. Okay. We have uncontrolled rapid growth. We can see this now with climate change and the consequences of that. Nature has controlled and slow changes. It's called evolution. It's had 3.5 billion years to get all these strategies right. And we need to take notice of these strategies. I'm going to finish off now by just saying a couple of things about whether biomimetic manufacturing is going to happen. I think it will. It makes economic sense. It certainly makes environmental sense, and it really is starting to happen. It is. We probably don't have any other choice. We've got to make this work somehow or other, and I can't see that biomimetic manufacturing is going to be an option. It has to be the only option, frankly, for us to do this. I'm going to basically stop here, and I want to actually just give you 2 comments to finish off with, two quotes. The first quote was from Leonardo da Vinci, that we shouldn't be inspired by a model other than nature. If we do, we're labouring in vain. He said this 500 years ago. So remember this. That people talk about biomimicry now as something we've just thought of. Here's someone who thought about it 500 years ago, and we've basically been doing this probably for thousands of years, but we haven't called it biomimicry. It's just a name we've put to things. It's a way of mimicking how nature operates. The other quote is from Francis Bacon: "Those who avoid new remedies can expect new evils, for time is the greatest innovator." Nature, again, has had 3.5 billion years to innovate. We've had 250, recent years since the Industrial Revolution to innovate. We're not doing it very well. We've got to go back and have a look to how to do it properly.